Hello and welcome to Introduction to C. Today, C programming language is widely used in embedded devices, and it powers most of the Linux-based internet servers. The Linux kernel is built using C, which means that C powers the core of all Android devices. So we can say that C code runs a good portion of the world's devices, which is quite remarkable. C is a compiled programming language. In this video, we'll briefly describe what happens when we compile C program. The compilation is a process of converting the source code into object code. It is done with the help of the compiler. The compiler checks the source code for the syntactical or structural errors, and if the source code is error-free, then it generates the object code. There are four entities involved in the compilation process: preprocessor, compiler, assembler, and linker. Let's see how each of them works. First, the C preprocessor, CPP, expands all macro definitions and includes statements, and anything else that starts with a hashtag, and passes the result to the actual compiler. The preprocessor just replaces some shortcuts you used in your code with more code. The output of CPP is C code. If you didn't have any preprocessor statements in your file, you wouldn't need to run CPP. The preprocessor does not require any knowledge about the target architecture. If you had the correct include files, you could preprocess your C files on one operating system and take the output to the other and pass that to the compiler. Here we can see an example of C code, a source file, and if we run either of these two commands, we obtain the preprocessed source code, which is also the C code. Note here that in this command, this is the name of our source file, and this is the output file with the extension I. The compiler effectively translates preprocessed C code into assembly code, performing various optimizations along the way. Since the compiler generates assembly code specific to a particular architecture, you cannot use the assembly output from one operating system on another. To see the assembly code produced by the compiler, we use this command, where this prog1.i is our input preprocessed source code, and the prog1.s is our output, which is basically a symbolic machine code. The assembly code generated by the compilation step is then passed to the assembler, which translates it into machine code. The resulting file is called an object file. An object file is a binary representation of your program. The assembler gives a memory location to each variable and instruction, and also makes lists of all the unresolved references that presumably will be defined in other object files or libraries. A typical object file contains the program text with instructions and data, constants and strings, information about instructions and data that depend on absolute addresses, a symbol table of unresolved references, and possibly some debugging information. To obtain an object code, we use this command. By using the symbolic machine code as our input file, to obtain the object code as our output file. Since an object file will be linked with other object files and libraries to produce a program, the assembler cannot assign absolute memory locations to all the instructions and data in a file. Rather, it writes some notes in the object file about how it assumed things were laid out. It is the job of the linker to use these notes to assign absolute memory locations to everything and resolve any unresolved references. The linker produces a binary executable that can be run from the command interface. We use this command to produce an executable code. Since it is an annoyance to call each part separately as well as pass the correct flags and files, GCC does this for us in just one command. So most of the time we just use this command to produce an executable from our source C file. The previous steps were also executed by this command, but are no longer visible to us, and all these files are automatically deleted.